Felix said, it's about generalized Langevin equations in time-dependent context. So I'm now at the University of Saarland, but this is the work that I've been doing in Luxembourg and in Freiburg during my PhD. And I would like to start with a very brief historical introduction of coarse-graining and I mean what is basically the basis of what I'm going to talk about then. And so basically the most standard model for coarse-grained that was historically proposed is for Brown in motion by essentially Langevin and Einstein. And the idea is, of course, as you all know, you have a heavy particle in a bath of light particles, and what Einstein proposed is just not to treat all the degrees of freedom of the light degrees of freedom in a deterministic way because there are just too many, but to treat them effectively as something stochastic, right? So Einstein, of course, did it on the level of the probability density of the position of the heavy particle. And what Langevin did a few years later is to say, well, instead of doing this, can I write an equation of motion for the particle itself in the form of a Newton equation of motion? And let's assume that I can treat all the collisions between the light particles and the heavy one as just a set of two forces, one being deterministic and being just a friction force that you know from hydrodynamic, and one which is a stochastic term, this psi term. And if you do this, then if you want to make it equivalent on the level of ensemble averages with the Einstein approach, then you have to ensure some statistical properties for this noise. And if you do this properly, then you can match the two approaches, and this is essentially the Langevin equation, right? And the Langevin equation, and also, of course, the Einstein diffusion equation is local in time. So the assumption is that the system, I mean, the whole thing is Markovian. And of course, this can be justified intuitively by the fact, especially if you have like a very huge mass compared to for the heavy particle compared to the other masses. So this was very, very fruitful at the time. It was really efficient to describe, to reproduce experimental data. So of course, then the field, because it was successful, the field of the mathematical field of stochastic processes was developed a lot in the later years by all these gentlemen, but also other people. And this helped to then describe more complicated processes with the same approach, saying that you have lots of fast degrees of freedom, and you don't want to deal with them. In a deterministic way, like explicitly, but you want to treat them effectively in a stochastic way. So, for instance, here you have a protein folding. You might want to describe the shape of the protein as you fold it. But you don't want to deal with all the atomistic details. If you want to, for instance, write an equation of motion for the shape of the protein, the case of phase transition here, crystallization can also be dealt with in this way. And it is, essentially, it's very efficient if you use the correct equations, if you do it properly. But on this level, I mean, in the level of what Langevin proposed, in the way he proposed it, this was only phenomenological approach, right? There was at the time no formal proof that the Langevin equation is actually justified from first principles from the microscopic dynamics. So this is, of course, well, a bit annoying. So what people did in the 60s was to essentially try to justify this from first principles. So the way they did it and was started with Robert Swansek in 1961 was using projection operator formalism. So assume you have an observable A that depends on all your microscopic degrees of freedom, and you have, you might have an experiment in which, well, it has it follows the black curve for its time evolution. You might want to distinguish between different contributions, right, to this. That basically contribute to this black line, for instance, a smooth contribution and a fast, noisy contribution. Right? So the way you can actually do it formally, mathematically, properly is using projection operator formalism. So I'm not going to go into full details of them, but just to give you the idea. So what you say is that basically you can use formally microscopic dynamics to express the time evolution of the observable. Just saying that because the observable depends on the time on the degrees of freedom well, then its time evolution is due to the time evolution of the microscopic degrees of freedom. This is just a chain rule that is essentially captured by the Liouvillean operator, and that you can solve then formally with this exponential propagator here. And of course, this form, this exponential propagator is true if the Liouvillean does not depend on time. So if the microscopic dynamics does not depend explicitly on time, but I will deal with the more complicated case later. Then assume you have a projection operator on the space of these variables, of these observables. So just assume you have one at your disposal. Then what you do then is to split the dynamics, so the dynamical operator, the exponential operator, into a projected part and an orthogonal part. And then the projected part, you leave it as it is, and the orthogonal part, you can rewrite it with what's called the Dyson decomposition, which can be split in two terms. And if you put everything together, then you have this equation, which gives you three terms for the time evolution of the observable. The first one being the projected part, the second one being well, essentially the friction part, as you will see, and which is non-local in time, depends on the past history of the process. And then the last one, which is completely orthogonal to the dynamics, as it's proportional to Q, which is the orthogonal projector. So now that you have this, well, this is nice and all fine, but you need to, well, if you want to have something more concrete, you need to specify the projection operator, right? So Swansek proposed one to deal with time-dependent densities, but what I want to talk about first is, well, not first, but in general in this talk, is the Mori type projection, which he proposed in 1965, and which is essentially a geometric projection, a linear geometric projection. So what he said is simply that, well, we have a space of phase space observables, and I can, in this space, define a dot product just by saying that it's the product of the average equilibrium average of the product of the two variables. Once you have such a dot product, then you can simply define a projection operator in the way you would do it in well, Euclidean geometry. And when you project any observable x, then you get something which is proportional to a being the variable of interest, the variable you want to write an equation of motion for. And the prefactor is just given by the dot product, essentially. Well, this sketch shows. So this is the idea, linear projection. And if you use this, then the whole decomposition I showed before is simplified in a quite simple form, right? So you have, again, the three terms. The first one being the drift term. It's linear in the observable A. It's local in time. The second one is the friction term. It's a convolution product. Again, of course, it integrates over the whole history. So that's the memory term. And the memory is basically governed by this memory kernel. And then you have a fluctuating term, which is, well, in the formalism, it's not, well, it's still analytic because you don't do any assumption on stochastic dynamics or anything like that. But it's just that in terms of interpretation, because it's fully orthogonal to the dynamics, if you have timescale separation, which is clear enough in your system, then you can interpret this as the fast contribution. So, and if you do all this formalism, you can also show that there is a proportionality relation between the memory kernel and the autocorrelation function of the noise. And all of this can be interpreted as this relation can be interpreted as a fluctuation dissipation theorem. And you can very easily see that this is a more general version of the Langevin equation, because the Langevin equation is recovered when the memory kernel is very narrow and becomes close to a delta function. And this is why we call it the generalized Langevin equation. But in general, the Langevin equation is correct in a certain asymptotic limit, which is when the memory kernel is very narrow. On top of that, you have the formalism gives you also a nice equation for the autocorrelation function, which has the same structure, but the fluctuating term vanishes. So what is important here is that, well, of course, that works for the case of Brownian motion when you look at the velocity of a particle, but in principle, it works for, well, it works for any phase space observable. There's very, very little assumptions that is a hypothesis which is needed for the definition of such an unobservable. So it can be used. This is a linear form that can be used for essentially any phase space observable, which is already interesting in itself. So at this point, it is nice, of course, but as you can see, this is using equilibrium averages. So if you use this formalism, then you can only look at equilibrium correlations. The next step is, of course, to ask the question, well, what happens to this if you look at non-equilibrium processes? So one way you can do it is just, well, let's start with to define the sort of system that we want to look at. Essentially, you have a system that you initialize in a certain state with a certain initial phase space distribution rho 0, and then you can define correlation functions using the propagators, saying that you start with a certain phase space point gamma, and then you evolve a variable x up to time t, a variable y up to time t prime, and you define the time-dependent dot product as just let's say time-dependent average of these of the product of these observables. Once you have this, this is a well-defined dot product. Then you can redefine the time-dependent projection operator in the same way that Mori did, except that the prefactor now depends on time. So it's as if the direction of the propagation of the projection in this sketch would change as a function of time. But it's essentially the same picture. And then formally, the Dyson decomposition can be, basically does not change much. There's very, very few change. And you end up with this equation of motion, which looks like the generalized Langevin equation, but you have a few changes. First of all, the drift term the drift coefficient gets a time dependence. And then the memory term is no longer a convolution product. You have a two-time dependence of the memory kernel, which makes it formally a bit more complicated to handle, but still it is there and there is not much more. And then you have the correlation, the fluctuating term, sorry, which is also there and which can again be interpreted as a noise if you have a timescale separation which is clear enough. And finally, one thing which is also interesting is that you still have this fluctuation dissipation-like relation between the autocorrelation function of the noise and the memory kernel, which is not obvious to interpret in non-equilibrium, but still formally it is there, which is also nice if you want to generate trajectories based on this equation, because that gives you information on the noise itself. And finally, you also have the same equation of motion for the autocorrelation function with the noise that vanishes. So this is for time. For the microscopic dynamics, which is time independent. So basically, when you have the Liouvillean that does not depend on time. So the next level then is to ask the question: well, what happens if I have some additional time dependence, right? For instance, if I have a time dependent microscopic dynamics. If, for instance, the Liouvillean, which is defined as the Poisson bracket of the Hamiltonian, gets a time dependence because, for instance, you have an external field that depends on time, or some time dependence in the interaction or something, then what happens? Well, essentially, formally, the propagator, which was exponential, is replaced by a time order exponential. Which, well, for simplicity, we just call it U, but it doesn't have the same nice stationarity properties as the exponential factor. But still, I mean, you can still use this propagator to define your time-dependent correlation function and your time-dependent projection operator. I mean, structurally, it's the same thing. And luckily, the Dyson decomposition also using these tools is the same. So we still have the three terms with the same structure. So we have, I mean, basically the formalism is safe. There is no, you can still write the equation of motion with the three terms which have this form. With the fluctuation dissipation theorem and with the autocorrelation function, which is like this. You can also see that in a nice way and just say that this you can treat this additional time dependence as an additional degree of freedom in your phase space, and just saying that you have a new, you can augment, well, extend your phase space by adding a new coordinate, and this phase space coordinate is such that s dot is equal to 1, such that you just follow time like this, you follow time, linearly. And you can treat the time dependence of the Hamiltonian as a dependence on this additional degree of freedom, and this helps to have a steady dynamics in the augmented phase space. And finally, you can also think of time-dependent observables, right? You can say, well, maybe my observable is also explicitly dependent on time. For instance, if you have non-equilibrium processes, you might have a variable that has a time-dependent average, and maybe you want to get rid of this average and redefine your variable by subtracting this average, or maybe by normalizing by the second cumulative or something. If you want to do this kind of things, then that defines new variables that are time-dependent. But still, you can also work in this augmented phase space and deal with this additional time dependence as a dependence on a degree of freedom. And formally, the same formalism can be applied. You still have these three terms that have the same shape, and you still have fluctuation dissipation theorem and autocorrelation function, the equation for it. So on the formal level, it's very nice because you can see that for a lot of processes, for a lot of observables, you can pretty much always put write the equation of motion for the observable in a generalized Langevin equation form, but a linear form, right? You can see that the drift term is linear, the friction term is also, well, of course, there is a time, history dependence, but still what's under the integral is linear, and you have the relation between the noise and the memory kernel. So the question, of course, is, in the context of Brownian motion, it makes sense to interpret this memory kernel as a friction term, because, I mean, you can think of Brownian motion, and so if A is basically a velocity, well, it sort of makes sense to interpret this as a friction term, but A can be anything, it can be any phase space observable. So the question is, well, what is the physical interpretation of this, right? What is this K when A, what is this K when A is something else, and what is this K if A is something you would not intuitively write a linear equation of motion for it? So we want to investigate this. So in the case of phase transitions, because this is typically the case in which you would not intuitively write a linear equation of motion for that. And we want to, well, have a look at what this K is, what this memory kernel is for phase transitions. So in phase transitions, what you might want to do is to write, I mean, if you want to look at the dynamics of it, is to write an equation of motion for an order parameter, right? What is the time evolution of an order parameter, which starts at a certain value in the initial phase and ends up in the final, with the final value at the final stage. And what lots of people do, and which is intuitively nice and quantitatively, it makes sense. I mean, it's a nice picture, is to write this as a nonlinear Langevin equation, which is driven essentially by a free energy landscape. So that would be the Langevin picture with the delta G, which is essentially what drives the process. And that's just Brownian dynamics, Brownian diffusive dynamics in this landscape. And you can also write this in the Fokker-Planck picture and looking at the time-dependent probability distribution of the order parameter, and you can sort of draw an equivalence between the two by adjusting the properties of the noise. This is, of course, nice in terms of intuition and understanding the physics of the process, but this is, I mean, these equations are clearly not very strongly justified from first principles. If you actually use projection operator formalism to show these equations, there are a lot of approximations that need to be done. So, which is maybe not the best to do. One classical example is the case of classical nucleation theory, where basically the free energy landscape is given by a surface term which prevents from a crystallite to grow, and a volume term that basically is the favorable term that creates a free energy barrier. and well, then you can intuitively understand what is the physics, the mechanism that drives this. But unfortunately, this is a good qualitative picture, but quantitatively, it's quite bad actually. And sometimes overestimate, sometimes underestimate the nucleation rates, and it's never in a very consistent way. So there were lots of explanations that were proposed over the years, and most of them, I mean, are perfectly fine and perfectly valid. But there is one that we want to challenge: is the actual shape of the theory, right? The Markovian shape of the theory. So can we use another equation to describe such processes? And because we know that the Morritt projection that we did, the linear projection, is exact, there is no approximation. The three terms are there, and there is no approximation. Let's try to use this, and let's try to understand what is the meaning of the memory kernel in this context, right? So this is exactly what we did. We don't want to understand 3 minutes. Okay, I'll be quick. We don't want to understand like what is the physical mechanism that explains the shape of the memory kernel, but only try to relate it to some experimental quantities that we can actually measure. So what we want in a classical phase transition experiment, you have this sort of shapes. The order parameter starts at a certain value, then waits in the induction phase, then you have a jump, and you can parameterize these curves by a sigmoid, which is parameterized by an induction time capital T and a transition time delta, which is the width of the jump. So in our model, we use this sort of model, and we want to interpret, I mean, to essentially relate the memory kernel as a function of, in terms of this delta and this capital T, induction time and transition time, right? So this is essentially what we do. So we have a way to evaluate the memory kernel in these terms. So for the case of this continuous jump, we can see that the memory kernel is essentially proportional to a delta function. So it's infinitely narrow. And here we have something Markovian. We end up with a Markovian description. But as delta, so the transition time gets larger, we have memory kernel that gets wider and wider as delta grows, right? So it indicates that maybe the time scale of the memory in this linear generalized Langevin equation is related to the transition time. So how much time the transition needs to occur once the jump happens. And we can actually do this for different induction time distribution and show that the width of the memory kernel, so the memory time scale, is really very strongly correlated to this jumping time delta, and it has roughly the same order of magnitude, right? So this is, of course, with the simple model of just using a sigmoidal function. So of course it's very simple. So we can test this on several models, on several simulations. I will be quick on this, but basically we have run a set of different experiments in which we have phase transitions, which are very different experiments, very different systems. And in all the cases we run the simulations, we can estimate the values for the induction time distribution and the transition time, which we did in all these cases. And we can also compute the correlation functions and compute the memory kernel then, and also sort of evaluate the time scale of the memory in these systems, and then have a look at what how they compare to this transition time. And this is what we saw. I mean, this is exactly, it confirms the theoretical prediction that is that it is very of the same order of magnitude as the transition time, right? So this is nice in terms of modeling strategies, because it just tells you that if you have a bit of information on these time scales from experiments or from just another type of knowledge, then you can write a linear generalized Langevin equation with a memory kernel that you can at least control the time scale. And that's already a good step if you want to go with this type of models for phase transition. So this is, of course, one example of how to use this linear generalized Langevin equation. But there are, we can think of many others. And to conclude, this is just a reminder of the main arguments. We have an equation of motion which is very compact and very general, that can be used in many contexts. The only question is what is the physical meaning of the different terms, and we have shown in one example of phase transitions what is the physical meaning of the friction kernel, for instance. And with that, I'd like to thank you for your attention.